Welcome to Earth Science, everybody. We'll start with Calvin and Hobbes. This was a comic strip that I was way into when I was in high school. Where Calvin, he's kind of a imaginative kid, so he has these daydreams and pretends they're really happening. So here he is going higher and higher and higher, saying, I suppose eventually the pressure in the balloon will be greater than the air pressure around it. And the balloon will. Let's think about a couple ideas here. You don't have to write this stuff yet. You'll eventually be writing things. I'm just going to use some blank space on this Cami doc. Let's think about a pool. And this still relates to that Kelvin thing. I'm not just bringing that up and then dumping it. We'll draw a side view of a pool. Shallow one, deep end, with some water in it, right? And I'm sure you've done this. You've played the game where you go down and try to get the rings. There's you swimming, right? You're going to go down here and get the rings. And when you get that deep in the water, you feel it. And you particularly feel it on your ears. Why? Well, you've got pressure on your head. You've got the essentially the weight of all of that water squishing on your head at that point. So what is it like as you come up and up and up and get higher up in the pool? It takes the pressure off, right? As a what feels like another random strange example, let's picture how our lives and the lives of a lobster have some similarities. I'm going to suddenly make this the ocean rather than a pool. If this is the ocean, and I have no idea how to draw a lobster. There you go. Doesn't matter. You're not drawing it anyway. Claw, claw. There's a lobster, right? A lobster is a creature that lives on a surface with a whole bunch of fluid on top of its head. In exactly the same way, you are a creature that lives on a surface with a whole bunch of fluid on top of your head. If we can see that similarity, you're going to start to get how pressure works as you move up and down in that fluid you live in. Now, the fluid that you live in is the atmosphere. You live on the earth. In fact, let's draw that. You live on the earth. I'll just write E to save some time here. And if we consider all the way up to the top of the atmosphere, with space being out here, this is the atmosphere. You live on a surface with a whole bunch of atmosphere on top of your head, just like the lobster. Think of the pool. Think of Calvin with his balloon. What would happen if you go higher in that atmosphere? For about a year, I lived at about 8,000 feet in Colorado. So rather than being close to sea level, which is what this diagram, which is not to scale at all, this not to scale diagram implies, right? If you're down here near the surface of the earth, how was it different when I moved up here into the mountains? Well, I have a whole lot of pressure, a whole lot less pressure squishing on my head up there in the mountains. In fact, it was a difficult adjustment when you first move up there from the lowlands, which we'll consider all, like the rest of the country pretty much, right? When you first moved up there, I had trouble. Like you'd get to the top of the stairs, and you like I had to sit down when I got up to the top of the stairs. You just my muscles felt exhausted. It'd be catching your breath because most of the atmosphere is actually below your feet when you're that high in altitude. Never mind getting way way up like people that climb mountains, right? This was about 8,000 feet. Um, so you get up there and there's less and less and less pressure. All of these little ideas are going to combine. Don't worry. If you're starting to think like, what is this guy babbling about besides what I always do? It's going to come to a point pretty soon here. So let's think about the lobster with all that pressure on its head. Let's think about you going down and getting the ring with all that pressure on your head. And let's think about Kelvin going up through the atmosphere. If you take a bag of potato chips down here at Earth's surface, I'm going to draw kind of what looks like a bag of potato chips, a very tall one compared to this person. At the potato chip factory, they dump some chips in the bag and they seal it at whatever air pressure is just existent in the atmosphere at the time, right? So what would happen if you drove those chips up the mountain? This actually did happen. I worked at a small grocery co-op. We would buy potato chips that were manufactured down at lower elevation. They'd drive them way up the mountain to 8,000 feet. And when they got up there, suddenly there's less air pressure pushing on the bag. So whatever air pressure was inside when they sealed them now, relative to what's outside, that same amount inside now can like push out more because the outside is pushing on it less. So we would open up these boxes of chips to put on the shelves, and they would be like sometimes exploded entirely, and sometimes like completely puffed out, completely rigid like a football. So why are we babbling about all this? Just like Kelvin's balloon, just like coming up in the atmosphere, or just like coming up from the bottom of the pool, or coming up from the bottom of the atmosphere, we've got to check out what happens as things rise in the atmosphere. And the reason I'm taking all this time to babble about all these weird examples is to try to get it to sink in. What happens as you go up is critically important to earth science. Critically important specifically to meteorology. Okay? I'm going to pause and rearrange the screen here and meet you back here in a sec. Okay, we're back. And now we're going to go back and review some of these moisture things, which you might say, hey, whoa, where were we with this whole rising thing? We're going to get there. But we got to combine those ideas that we learned with the rising with some of the humidity things that we've already done. Ideally, if you've been doing everything in order, this is a review. If not, well, here it is, I suppose, right? But you should probably go back and make sure that you're lined up with where we've been. Dew points, as you did in the lab for dew points and relative humidity. Dew point is the temp needed for condensation. All right. If you don't know where we are in this document, I can zoom out real quick. We're up here. We're gonna want to fill in this box, and then we'll wrap it all up, pull it all together um, at the end. Temp needed for condensation. So you did a lab with these aluminum cups. So easy, where you just said, if I need to find the dew point, if I need to find the temperature for condensation, I'm just going to make this cup colder and colder and colder until I see condensation. Then I know it's there. I know I've reached the dew point because the dew point is that temperature. So you put a thermometer in, you put ice in and stir it until you got condensation. And boom, there we go. That's the temp needed for condensation. That's the dew point. That's the temperature that we reach to get condensation. The relative humidity, we're ignoring how this is really a very complicated idea. And for us here in Regents Earth Science, we're going to say this is the percentage of water vapor in the air. Keep it simple. It's more complicated than that in real life. We don't have to worry about that. Condensation and evaporation are both phase changes, which means between our three states of matter, solid, liquid, and gas, this is a transition from one to the other. Condensation will be a phase change from gas to liquid. So take some of the water vapor that's in the air, some of the water molecules that are in between my hands right now as a gas, and turn them into a liquid. Those water droplets that magically show up on this can, that's condensation. Evaporation is the opposite, phase change from liquid to gas. All day long, all I did was accidentally spill some water on the counter, and like, since it's so dry in here, in a period or two, it all dries up. Does it disappear? Does it cease to exist? No. It's just liquid water on the counter, and it turns into water vapor in the room. Lastly, saturation is when the air is full, which I'm putting in caps, that's the critical word here, when the air is full of water vapor. Maybe underline that word. That's the one right there. Now, okay, can we get these definitions? That'd be great. But where the magic really is with this is, can we use all of these like in sentences and see how they start to interrelate to each other? For example, if the air has reached saturation, if the air is saturated, are we clever enough to know then what the relative humidity would have to be at that point? When the air is full, since relative humidity is a percentage, when we reach the point of saturation, that means that the RH, I should be typing rather than trying to write, the RH equals 100%. The air is totally filled. The humidity is 100%. There's no more capacity for water as vapor to get into the air. At that point, it's got to start condensing. It's got to start turning into a liquid. So if you're extra clever, you would say, well, since this is what's happening, since the air is full, since we're getting condensation, that must mean that the temp equals the dew points. Whatever the dew point is, the temperature's got to be the same. The humidity got to 100%. Condensation is taking place. The air is saturated. I realize that's a lot. I realize those are very chewy, dense, vocab rich sentences. But that's the job. That's what we got to start getting comfortable with, interrelating all these, and why we've done it in multiple different note sets so that we can start to try to wrap our heads around it. So now let's combine our friend Calvin with his balloon, or me with the potato chips in Colorado, or you swimming up in a pool and going down and seeing how there's more pressure at the bottom and less as you work your way up. This all will combine to get us a critical idea here in nurse science, which is that for various reasons in various different circumstances, in fact, in normal circumstances, air is going to be rising. Maybe it's happening because, like we learned in energy, the sun hits the land, the sun hits the water, and the land heats more because of its lower specific heat, and therefore that air is going to rise there. Maybe it's because it's just hitting a mountain range and rising, or hitting the Tug Hill Plateau or rising. Maybe it's because of what pressure systems are in town. Maybe it's because of what fronts are blowing through. There's a lot of reasons out there, but again, in fact, in normal circumstances, air rises. It's unusual for air not to rise. It's unusual for there to be air trapped at the surface with warmer air aloft and everything sitting very still and stable. It happens, but it's not the normal set of circumstances. The normal set of circumstances is that for whatever very different reasons that are happening that day, air rises. So here we go. We're going to begin something that you are going to say enough times that it will drive you crazy. I don't like that auto. Step one, air rises. We're going to do a list and we're going to work our way from the bottom up because this happens as air rises. Step two, as air rises, let's think about all this jazz that we did at the beginning. What does Kelvin say happens to his balloon? What did I say happens to potato chips? What did you have experience in terms of the pressure on your ears? As air rises and it goes up, it gets up into areas that are lower and lower pressure. So if I took all of the air that's sitting on top of the whole entire village of Pulaski right now and had it start to rise up through the atmosphere where there's less and less pressure, what happens to the size of that parcel of air? There's less and less pressure on it. So like the potato chips, it can get bigger and bigger and bigger. So two, it expands. And as it expands, because of how temperature works, and this can get a little confusing. If you don't quite get this right out of the way, don't worry about it. As it expands and the molecules are like banging into each other less often, they have more space between them, they get lower energy. They're shaken less. And that is what temperature is. So it cools. It's just a function of this is like it's chemistry. So you'll get into it next year. Gas laws, why this happens. We'll just say it happens. So there you go. When air rises, it expands and cools. When air rises, it expands and cools. When air rises, it expands and cools. In the pre-COVID days, I would make people say this so many times that it kind of turns into a joke. People have literally come up to me in the street that have graduated and said, expands and cools, because they know that I ask it that often. You're not making it through the end of this marking period without these two in your head, like verbatim. When air rises, it expands and cools. It's at the core of why weather happens, why clouds form, which turn into precipitation, which turn into all the varied forms of weather. It all comes down to air rising, expanding, and cooling. So these two, say it 100 times. That's your job. I didn't make the people in class say it 100 times. They said it like 10. If 10's enough, then cool. When air rises, it expands and cools. You're going to see all these questions in a minute. And guess what? The answers to all of them, cloud formation is likely to occur because rising air expands and cools, expands and cools, expands and cools, expands and cools. Why is this important? Step three. I don't know why it does this, like makes it number one there. Kind of frustrating. Step three. We'll do it in red. It will eventually cool and cool and cool until we start using some of this vocab up here. It's going to cool until it gets to that temperature you need for condensation. It cools to the dew points. That's the temperature at which condensation occurs. So now we're getting somewhere. Step 4, verbal. I'm going to put way over here because there's a lot to write. Step 4. Cools to the dew points. That is where condensation occurs, which means the relative humidity is 100%, which means the air is saturated. All of those things like go together. That happens when we cool to the dew point. That's why expanding and cooling is critical in this rising air. Because once that happens, we get to form clouds. As soon as you hit the dew points, clouds form. That's it. That's what we're doing here. That's what we're talking about. Air rises, expands and cools, hits the dew points, condensation occurs, humidity is 100% with full air, and clouds form. That little formula right there, that's got to get into our noggins. There's no way around it. We got to go and talk, and you'll be doing this big scary cheat sheet pretty soon. And we got to talk about how cold fronts make the air rise, and how warm fronts make the air rise, and how plateaus and mountains make the air rise, and how low pressure systems make the air rise. And it's all the same thing over and over and over again. And it all boils down to this, that when air rises, it expands and cools. I tell everybody, in fact, if you know anybody, again, the last 2 COVID years, I didn't really hammer on this as much. But if you know anybody that took this course that like is either just graduated and maybe within that 3 or 4 years, graduated to just like out of college, or I'm sorry, out of school for 2 or 3 years, and they took my course, ask them, what happens when air rises? Text them right now. And they're going to tell you it expands and cools. They have to say it that much that you will remember this for years. So jam it in your head now. It's coming at you again and again and again and again. All right. Your job is to jump onto these questions right here. I didn't necessarily collect these, but try them first. And hint, hint, the answer to all of them revolves around the idea that it expands and cools. In fact, you know what? Hit pause right now and do them, and then I'm going to record the answers. So 1, 2, 3, pause. Go ahead and do all those questions, please. Okay, you did your questions, right? Welcome back. You've done them. Air hits a mountain and rises up. We'll talk about this in greater detail. It's like a machine for creating clouds and weather because when air rises, it expands and cools. Choice 3. Rising air expands and cools, causing the water vapor to condense. Weather along most fronts. We haven't done it yet, but we're going to get there. How cold fronts and warm fronts make the air rise, and then it expands and cools. Condensation, dew points, clouds. Choice 3. Rising and cooling, causing water vapor to condense. This one we already did. Rising air expands and cools. Seeing why I say this so much? You got a 10-question classwork, like a usual one in a minute. I had to go through 11 regencies to find 10 questions. It's like, so take that as a pretty solid sign that on the regents there will be a question dealing with expanding and cooling as air rises. Like this one, 20, what atmospheric conditions are necessary for condensation? We need, I believe this one was 3 also, saturated air and equal temperature and dew points is correct. Can't be unsaturated. You're not going to form any clouds that way. And this one has the dew point much lower than the temperature. That would not form clouds either. In fact, that wouldn't be saturated air. Number 1 is the thing that just doesn't happen. In case I didn't mention this, right? In case you didn't realize this, newsflash, clouds are liquid water. Not everybody knows that. So let's throw it out there. It's condensation. You form water droplets. Clouds are liquid water droplets. Now, they're very fine, small ones that are light enough to stay suspended in that rising air until they get heavy enough to fall down, in which case we call it precipitation. But they are, in fact, a liquid. So make sure you keep that in mind. It's not water vapor. You can see through water vapor. There's water vapor in between me and the camera right now. Can't see it, though. Clouds you can see because they're a liquid. So let's just make sure we got that point in mind. 74, identify a weather instrument that can be used to determine the dew point. You should have done this lab already. We should be getting comfortable with the fact that this is a psychrometer. Though sometimes I understand that the spelling is a little bit tricky. PSYCHRO meter. What is the relative humidity at the base, bottom of the cloud on the windward side of the mountain, or in every cloud ever that's ever existed? The relative humidity, since it's liquid water, since you're going through condensation, since you're forming clouds, is 100% all the time, everywhere, every day that there's clouds. Explain why air cools as it rises up the mountain. It cools because there's less air pressure squishing it into a smaller space. As it rises, it expands. You can do, in fact, you're going to do an earth science experiment with this at some point in your life. How about we do compresses first? Pump up a bike tire or a basketball or something. When you're pumping and you're holding the needle in there or the little contraption on the bike, you're going to feel it heating up. You're compressing the air, compressing worms. And then if you expand it, you can feel how it's cool. If you turn on a air compressor and let the air come out of it, it expands, it cools. It's also how your fridge works with condensers. It takes advantage of these rules. It's gas laws. Again, you'll do it in chemistry next year. Expanding goes with cooling, compressing goes with warming because of what you're doing to the air molecules. That's kind of what they ask would be here. If we're all very comfortable with the idea that rises, expands, and cools, well, what about B? If it's going down, then the temp increases, it warms. What does that do to humidity? Well, as it rises, you're dropping down the temp to the dew point, which makes it more and more and more humid until the point that they're the same and they form clouds. As it sinks and gets warmer, 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 you're making it go further away from the dew point, which is what like getting dry is. Just like the question on the lab that dealt with why is it so dry indoors? It's dry indoors because you're making the relative humidity and temperature go further and further apart. So the temp increases, but the humidity, and I believe that's what they asked, right? Yes, decreases. All right, thanks for sticking with me on all that, folks. Next thing in the survival guide is a quick 10-question quiz. 9 of them are what happens when air rises, it expands and cools. One of them is what happens when air sinks. You can bang that out pretty quick. Good luck, and thanks.